As we said, CDMA did have its fair share of problems before it became a cellular standard. We'll look at two of those in this lecture, but specifically we'll focus on the first one that we point out. And we'll start that off by looking at what's called the near-far problem. But first, suppose we have a bunch of transmitters, like a bunch of cell phones, and we're all transmitting in close proximity. So as we said, under a CDMA scheme, they're all going to be transmitting on the same frequency and at the same times. And so with CDMA, they have different codes, but still this will cause some interference. So there will be inevitable interference if everyone's transmitting at the same time. And we have to overcome some of that interference here. So now, in this picture, in this diagram, we have all these transmitters in very close proximity to one another. But this problem gets exacerbated when we have transmitters that are different lengths and distances away from the recipient tower. So we could have one transmitter in your car, maybe, and another transmitter that's behind a few trees and much farther away from the cell tower. And so we say that this guy is going to have much better channel quality than this guy over here because there's trees and there's a lot more distance in between. And the distance as well as objects in the path that obstruct the channel lead to different levels of channel quality. And this guy's going to have a degraded channel quality relative to this guy. And so this is known as the near-far problem. Is that we have different levels of channel quality depending upon how far we are from the base station. So before we look at the solution to the near-far problem, we first have to define how we go about measuring power. So how do we measure transmit power? We need a way so that if you put it on a ruler, rather than having inches, we'd have some other quantity. And the quantity that we use is called the watt, and that is the standard unit for power. So a watt is actually much larger than anything your phone would ever transmit. Your phone transmits is on the order of milliwatts instead of on watts, and a milli is times 10 to the negative 3. So it's 1,000th rather than kilo as we saw before, which was thousands. Milli is thousandths. So the levels of your phone transmissions are on the orders of milliwatts. So let's suppose that the first car over here is transmitting at 20 milliwatts. And he's transmitting to the base station. And as we said before, we have attenuation. And by the time it gets there, it's down to 10 milliwatts. So it's cut in half by the time it gets to the base station. But now, as the near-far problem would tell us, this car, who may be also transmitting at 20 milliwatts, by the time he gets to the station, his power is all the way down at 2 milliwatts. Because not only does he have more attenuation because he's a farther distance, but there's also trees and objects obstructing the signal's path. So it's weaker by the time it gets there. So we want a way to be able to equalize the power levels at the recipient. So at the base station over here, we want to be able to make these two levels the same. We want these two to be the same. And so we need to boost the transmit powers. And that's the way that we do that. And so there's an algorithm that does this, and it's a very simple algorithm, and we'll look at that right now. And basically, by the time this signal gets over here, as we said, it's cut in half. Because if we take 20 divided by 10, we get 2, which indicates that this is twice the power at the recipient. And now, suppose that the receiver wants to see 5 milliwatts. So it doesn't even want to see 20 milliwatts or 10 milliwatts or anything. It wants to see 5 milliwatts. So this transmitter, even by the time the power gets there, is still too high. And this transmitter is, on the other hand, too low. So this 20 over 10 gives us a factor of 2, which tells us how much this guy has decreased by the time it got to this recipient. So basically, the tower is going to tell this car right here, this transmitter, it's going to tell him to transmit rather than at 20 milliwatts. It's going to say, okay, well, I know that your signal gets cut in half by the time it gets to the receiver. Then I want to receive at 5 milliwatts. So I want you to transmit at twice 5 milliwatts. So 2 times 5 milliwatts, which is equal to 10 milliwatts. So the tower is going to send a signal back that says send at 10 milliwatts. And so the idea is then if this guy changes to 10 milliwatts, hopefully this signal will then cut down to 5 milliwatts by the time it gets to the receiver. It may not be exactly certain. You may have to iterate a few times before it gets exactly to the desired, but you get the basic idea. Now, on the other hand, with this transmitter over here, he starts at 20 milliwatts, and by the time he gets there, he's down to 2 milliwatts. So 20 divided by 2 is 10. So it's a factor of 10 reduction rather than just having it's dividing it by 10 by the time it gets over there. And as we can see, the received power in this case is less than this desired received power. So they take this 10, this factor reduction, and say, well, transmit at 10 times whatever I want to receive, or 5 milliwatts. So he's going to say, okay, transmit at 50 milliwatts. So while this guy's transmit power goes down, this guy's transmit power goes up to 50 milliwatts. And the hope is that if he sends at 50 milliwatts, then by the time it gets down here, this will be at 5 milliwatts as desired. So we can rearrange this equation just a little bit to make it a little more convenient. If we just take this example right here, let's say we have this 20 divided by 10 times 5, which is going to give us our result. So this, as we said, is the transmit power, this is the received power, and this is the desired power. So if we take this and let's rearrange this and put the transmit power out front. So we can say that this is equal to 5 divided by 10, because we're multiplying, so I can just move over. I can move any of the terms. So 5 divided by 10, and then we'll multiply that by 20, which is the transmit power. So we can take this as a constant term, because the 5 milliwatts is constant, and whatever is received at is constant for this time. And that gives us how much we want to multiply the current transmit power by to get the next transmit power. And that gives us the basics of the transmit power control algorithm, where we basically say that the next power is equal to this thing called the ratio times the current power. And the ratio is this guy down here, this 5 over 10. That defines the ratio. So if we look at that again for this example very quickly and see what that tells us over here, we can take this and rearrange. So we have 20 divided by 2 times 5 instead. And we said, well, we want to take the desired power of 5 and divide that by the received power of 2 and multiply that by the transmit power of 20. So now this ratio is 5 halves rather than 5 tenths. Notice that the ratio tells us whether the transmit power in the next iteration is going to be higher or lower. If the ratio is less than 1, as it is in this case over here, then it means that it's going to be lower next time. And if it's greater than 1, it means it's going to be greater, as it is over here. And in the case that it was the same as 1, which is where we want to get to eventually, it would stay the same.